Welcome to Thermodynamics. We're going to cover part 1 in 2 videos. So this is part 1A, and here are our objectives for today. We're going to learn the 3 laws of thermodynamics. We're going to review enthalpy. So we touched on enthalpy a little bit in solutions when we covered the heats of the reaction for solutions. We're going to understand spontaneity. So up to this point, we've talked about how fast a reaction will go or how far it'll go. So how fast was kinetics, and that's going to be driven by the reaction order and the overall rate of that reaction, which is something that's really hard to predict. So that's very much an experimental science. And then we looked at the extent of a reaction. So equilibrium, we spent quite a bit of time with equilibrium reactions, how far a reaction will go. In thermodynamics, we are going to be removed from those two, and we're going to talk about the why. Why do some chemical reactions happen spontaneously and others require energy or some other type of intervention for us for that reaction to happen? We're going to understand spontaneity, and then also we're going to go back to that term entropy that we introduced in this chapter for solutions, and we're going to really dig into entropy. This is the first law of thermodynamics, that the total energy of the universe is constant. And so when we have solar panels, for instance, on our roof, we're harnessing the electromagnetic radiation energy that's coming from the sun, and we're turning that into electrical energy. So we're not really generating energy, we're just transferring energy. And so the total energy of the universe is going to be constant. So when we think about these different energy terms that we're going to talk about in relation to chemical reactions or state changes or any kind of process, this is all about energy transfer. So I'm looking at energy from either a system transferring to the surroundings or energy from the surroundings transferring back into the system. So we're going to be looking at changes in energy in this chapter. If we think about spontaneity of a chemical reaction, we all are familiar with reactions that happen spontaneously. So this would be an example of if you have a car and you grew up on the East Coast, or even just out here on the West Coast, where there's a lot of salt present in the air, or they salt the roads in the winter, then you're going to see this happen even quicker than it would normally happen. But iron will rust, and iron will rust over time, and it only needs water and a little bit of salt in the air for that to happen. And so that's a spontaneous reaction. But this can happen slowly or it can happen quickly. So it depends upon the conditions. The rate doesn't affect the spontaneity. This reaction is going to happen whether it happens slowly or whether it happens really quickly. Another example of that would be both diamonds and graphite are made up of carbon. Diamonds are super hard substance, while graphite is a relatively brittle substance. And even though they're both made up of the same atom, they're both made up of carbon atoms. The difference is in the degree of movement between those carbon atoms that make up those structures. And so diamonds are very fixed. They're in a very constrained lattice structure where the carbon atoms are constrained amongst themselves in a plane, and then between the planes they're also bonded together, and so each carbon atom is really fixed in place. If you think about solids in a lattice where we have points all around that atom that are going to be constraining its movement, and so that's what a carbon atom is in a diamond. It's very constrained. But in graphite, you have carbon atoms that are constrained within a plane, but then those planes have freedom of movement between them. And so there's a lot more movement in carbon in graphite than there is in carbon in a diamond. And that's what we see in its physical properties. The spontaneity of this reaction is that diamonds are slowly turning into graphite. And so that's a spontaneous process for carbon that's in a diamond form to turn into carbon in a graphite form. And that is happening spontaneously. However, that is an exceedingly slow process. And so over our lifetime, if we have a diamond, we're not going to see that diamond turn into graphite, but that is a spontaneous process that's happening without any intervention from us. So that's a spontaneous process. A non-spontaneous process is, if you think about the reverse, if I want to go from graphite to diamond, it's not that that is impossible. It's just that that may require more energy and more intervention than we are able to do. And so a lot of processes or chemical reactions that are non-spontaneous, we can actually force them to happen, but what we're doing is we're coupling them maybe with a spontaneous reaction, or adding energy in to get that non-spontaneous reaction to happen. And we'll talk about more about that as we go through this chapter. Okay, so let's back up and talk about really quickly one of the energy terms that we've already learned, and that's enthalpy. So remember, enthalpy was large H, and this was the heat. So this is an energy term, and it deals with heat, which is thermal energy. And we said that H is a state function, meaning that it doesn't matter how my energy has transferred. The only thing that's going to matter is what is my final state and what was my initial state. And so oftentimes we're looking at the change in enthalpy. So anytime you see this triangle here, or this delta, this means change. And it's going to mean change from some initial state to some final state. So I always have final minus initial. That's going to be my change. And whenever you see delta, especially when we're talking about energy terms, it's always going to be final minus initial. So my final energy state minus my initial energy state, and then I'm looking at that transfer of energy. Now we had two different signs for H. My delta H could be negative, or my delta H could be positive. And that tells me something about that process or chemical reaction. So if it's negative, then we said that that was an exothermic, meaning it emits energy. If it's positive, then that's endothermic, meaning that it's absorbing energy. And we're applying this to the system, whatever it is that we're looking at. If I have a chemical reaction, that chemical reaction is my system, everything else is the surroundings. So this energy is leaving the system here and going into the surroundings. So the surroundings are gaining energy, the system is losing energy. So when we think about, especially in this chapter, we're thinking about energy transfer, we're going to have to define what is our system and what is our surroundings. Where is that energy going? So we can apply the same thing to the energy of the universe. The energy of the universe is simply the energy of the system plus the change in energy of the surroundings. And the first law of thermodynamics tells me that that is always zero. So this is my first law. My total energy of the universe is not changing. So enthalpy is one component of this. Another component is entropy. Let's explore this idea of spontaneity. This is independent of rate of a reaction. Think about diamonds. And it's not dependent on H. So enthalpy doesn't tell me anything about the spontaneity of a chemical reaction. It can favor a chemical reaction or it can unfavor a chemical reaction, but enthalpy itself doesn't give me any information on the spontaneity of a reaction. So that is the second term that we talk about in thermodynamics, entropy. All right, so my criteria for a spontaneous process or reaction is entropy. So entropy is going to dictate whether something is spontaneous or not. And it's this interplay between enthalpy and entropy that is going to give us a complete picture of the total energy that's happening in a process or a chemical reaction. So a spontaneous reaction, no outside intervention, meaning that it's going to happen regardless of what I do. A non-spontaneous reaction is going to require intervention. And that intervention is usually in the form of adding energy. I can also couple a non-spontaneous reaction with a spontaneous reaction, and the spontaneous reaction supplies the energy for the non-spontaneous reaction to happen. We'll talk about this more because we have a perfect example of that in developing bombs. Why can we say this? Remove enthalpy from spontaneity, because we just talk about like how reactions are favored. So if I have an exothermic, meaning I'm emitting energy, this is going to be favored. So this is going to favor that reaction happening. An endothermic reaction, anytime you have to add energy to a system, this is going to be unfavored. So you would think, well, if I have an exothermic reaction, then those are always going to be spontaneous, right? But the answer is no. So sometimes I can have an endothermic reaction that's also spontaneous. And if you think about water evaporating. So if I look at my phase changes here, solid to a liquid to a gas. If I go from a solid to a liquid, I have to add energy. I'm going to have to add thermal energy to that system. Think about taking an ice cube from your freezer, you set it out on the counter, it's going to start melting because it's absorbing heat from the surroundings. If I have a liquid and I want to go to a gas, that liquid molecule is going to have to absorb enough energy to move to the gas phase. And so gases have lots of kinetic energy, lots of movement, whereas a solid has a very little movement. Right? So as I move through here, I'm having to add energy in. If I go all the way from a solid to a gas, sublimation, that requires even more energy. So all of these are going to have a delta H sign that's positive, meaning that they are unfavored from an enthalpy standpoint. If I go in the opposite direction, so I go this way, I'm condensing. I'm taking something that's really high energy and I'm forcing it into a state where it has lower energy. And so that is going to have to release energy. So this is going to be favored from a enthalpy standpoint because I'm emitting energy. It's going to have a negative sign. Same here. My delta H here is also going to be negative as I freeze or deposition, gas all the way to a solid. Now I've had to release a lot of energy. And so if I'm going this direction, solid to a liquid to a gas, this is going to be unfavored from an enthalpy standpoint because my delta H is positive for all of those processes. If I go this direction, now I'm going to be favored from an enthalpy change because they're negative, right? So I'm releasing energy. Okay, this is what we would call endothermic, and this would be exothermic, where I'm releasing heat. That's going to be an exothermic process. So not everything that is favored from an enthalpy standpoint happens spontaneously, and not everything that's unfavored from an enthalpy standpoint doesn't happen spontaneously. So if we look at the evaporation of water, what I see with the evaporation of water is I'm moving from the liquid to the gas phase. And so we just talked about how that is going to require energy. That's endothermic phase transition from an enthalpy standpoint, but water will evaporate spontaneously. And so there must be something else that's driving the spontaneity of that process. If I leave water out long enough, I don't have to add, if I add heat, for sure it's going to happen quicker. But if I don't add heat and I just have a pot of water out on the counter, it's eventually over days and maybe weeks, it's all going to evaporate. And so that's going to happen spontaneously, even though I haven't done anything to the system. And it's unfavored from an enthalpy standpoint. But what I'm doing is when water molecules move from the liquid phase to the gas phase, I'm increasing the movement of those molecules. And so they have more degrees of freedom, more ability for them to move. They're going to be dispersed randomly as opposed to in a liquid where they still have some intermolecular forces between those water molecules that are holding them together. So this would be a spontaneous process that's unfavored from an enthalpy standpoint, which takes us to the second law of thermodynamics. And the second law of thermodynamics deals with entropy. So entropy is also a state function, just like enthalpy, but entropy is another energy term that's a little bit more abstract. So enthalpy is heat, and we can feel when we have an energy exchange that happens in the form of heat. Entropy, we can't really feel it. It's more of a state of being. And so the second law of thermodynamics states that for any spontaneous process, so remember we're going to link the criteria for spontaneity not to enthalpy but to entropy. For any spontaneous process, the entropy of the universe is going to increase. So entropy is an energy, and it's the second energy that's going to drive. So there's two energy components that we're going to think of in terms of a chemical reaction. The first one is enthalpy. The second one is entropy. And it's the criteria for spontaneity of a chemical process, think state changes, or a chemical reaction. So products, reactants go to products. So both of those, we're going to apply these energy terms to. Entropy is a measure of disorder. We could define it as dispersion, a measure of randomness. We could define it as more degrees of freedom of movement. Your entropy is really going to be changes that affect something, that affect the disorder. So when I order something, I take my drawer that's full of mismatched socks and I match my socks and then I fold them really neat and I put them back in my drawer. I'm fighting entropy. So I basically ordered that. If I don't do anything over time, I'm going to be in that drawer pulling socks out and putting things away. If I don't put the energy in to refold them and remate them and all that, then they're eventually going to be just a cluttered, disordered mess like I started with. And so that is entropy. Entropy is the the propensity of a system or a reaction to move to a greater amount of disorder, more degrees of freedom. Solids, as solids move from a solid to a liquid, those molecules have more degrees of movement. And so that is going to be favored from an entropy standpoint. If we think about our water evaporating, I have water in the liquid phase, still constrained because it has those intermolecular forces. As it moves to the gas phase, those molecules are I'm increasing their degrees of freedom of movement significantly. And so that's what's favoring the evaporation of water, and that's what's driving the spontaneity of that reaction. So it's not the enthalpy. I'm still having to put energy into the system in terms of thermal energy, but the energy I'm getting out in terms of entropy is going to be much, much greater because my entropy is significantly increasing as I move from the liquid to the gas phase. So entropy is this way of tracking this measurement of randomness or disorder or dispersion or freedom of movement. Anytime I'm increasing these components, then I'm increasing the entropy. So we're going to be looking at entropy just like we did enthalpy. It's going to be big S. And so this is also a state function. So I'm going to be looking at the change in entropy as a measure of the final state minus the initial state. So what was my initial state? Was this a liquid? And then it moved to a gas phase, then this is going to increase. And so my entropy is going to be favored. For any spontaneous process, so just to reiterate this, the entropy of the universe is always going to increase. That's my criteria for spontaneous processes. Before we move into too much with entropy, I want to go back and just talk about rates of chemical reactions. So at the beginning, I said that kinetics and equilibrium are separate from thermodynamics. And I just want to kind of hammer that home. If we think about an energy diagram where I have energy and let's say I have a chemical reaction. So this would be reaction progress. I could have my reactants here. And if this was an endothermic reaction, my products would be up here. So there would be an increase in energy. So I could take where my products were from where I started. This is going to be my change in enthalpy for that reaction. And this is going to be positive because my products have more energy than my reactant. So I've had to absorb energy into that system. So this would be an endothermic. It's going to be unfavored from an enthalpy standpoint. Now, if I think about kinetic, what's happening with the reaction rate of this? If I have a really slow chemical reaction, I could have a really high activation energy. This was my energy barrier for the chemical reaction. And this is going to control my rate, but it has absolutely no effect on the thermodynamics. So I could have a really fast, I could have a really slow reaction with a really high activation energy. I could have a very fast reaction with a low activation energy. This would be faster. But my thermodynamic parameters are going to be unaffected. So rate and thermodynamics, this energy transfer, are different. So this is an energy, but this is the energy that I'm going to have to put into that system to overcome this activation energy. The energy we're thinking about in terms of thermodynamics is this transfer of heat, endothermic or exothermic, and entropy. Have I increased the disorder, dispersion, randomness? Have I allowed more freedom of movement in my molecules? If that answer is yes, then I've favored it from an entropy standpoint. So what happens if I add a catalyst to this? Are catalysts going to affect my thermodynamic parameters, these energy parameters? What a catalyst will do is if I add a catalyst, let's say to this reaction here, it's going to lower the activation energy. So I'm going to add a catalyst. Now I've lowered this activation energy. I've increased the rate of my reaction, but I still have no effect on my thermodynamics because I'm only looking at a state function. It doesn't matter how I get from here to here. I'm only going to look at the difference. So that is the definition of a state function. It also doesn't matter if this reaction happens in 1 step or 5 steps. So if I have a 2-step reaction, let's say I have 1 step that goes here and I have an intermediate, and then I have a second slower step that goes here. Now I have 2 activation energies here, EA1, actually this is my slower step, and EA2. it still doesn't matter. This isn't going to change. So it doesn't matter if it's one step, if it's a really slow step, if it's a fast step, if I add a catalyst, if I have multiple steps, none of that is going to affect the energy of this reaction. So this is all rate stuff, right? This is kinetic. It's going to affect how quickly the rate of that reaction, how fast that reaction is going to occur, but it's not going to have any effect on the thermodynamic parameters that we're going to talk about. So it's not going to affect my heat of my reaction. It's also not going to affect the entropy of my reaction. So it doesn't affect the spontaneity of the reaction. Just because I have a fast reaction does not make it spontaneous. All right, so going back to entropy, there's a reaction that was introduced for entropy, and it looks like this, ln of W. That's a K. So this is not little k rate constant. This is something called Boltzmann's constant. It's 1.38 times 10 to the minus 23rd joules per Kelvin. This W, it's a number of energetically equivalent ways to arrange a molecule. And so as W goes up, your S is going to go up. And Boltzmann's constant is going to introduce your units here. And so you'll notice that my units are joules per Kelvin. So entropy is always going to be given to you in units of joules per Kelvin. If you think about enthalpy, what our units of enthalpy were for enthalpy are going to be in kilojoules, whereas entropy, I'm going to be in joules. So different units, they're still energy units, I'm still in joules, but now this is kilojoules and this is joules. So when we have a calculation where we're using both enthalpy and entropy, we need to pay attention to these units because we're going to have to change the units. So let's look at your book spends a lot of time talking about these gases in these sealed vacuum containers. And so I just want to kind of review this really quickly. So your book introduces entropy, and then it promptly goes into this really confusing, at least I think it's confusing, description of gases in these flasks and how I can have these different macro and micro states and all this. And I just kind of want to touch on this a little bit. So I have these 4 gases and I have them in a flask here. And this means that they are connected, and then I can cut off and cut on the connectivity. So I can open this up and these gases can flow over to here, or I can keep it closed and keep the gases on this side. And so what gases will do spontaneously is they will disperse. And so if I were to pop a balloon in this room that I'm in, and that balloon had helium in it, those helium molecules would disperse throughout the room. So they would take up the entire volume of the room that's in here. And so they would disperse, and that would be spontaneous, but there's no change in heat of that reaction. So if I think about enthalpy, this would be an area where there would be 0 change in enthalpy because they're not transferring energy to the surroundings, they're not absorbing energy from the surroundings in terms of heat. But what they're doing is by allowing those gas molecules to disperse within the room, I'm allowing them more degrees of freedom of movement. And so I'm increasing their entropy. I haven't changed the enthalpy at all. And so if you think about these 4 gas molecules that are in this glass container here, I can have all 4 of them in one side. I can have, that would be state A. I could have all 4 of them in the other side, and that would be state B. Is that going to happen though? What really is going to happen is I'm going to have them dispersed between the 2, and they'll do that automatically, and they'll do that every single time. And so if I think about, if I have each of these as a unique gas, I have more ways for these gases to be dispersed. I could have, let's say I number them 1 through 4. I could have gases 1 and 4 in flask A and 2 and 3 in flask B, or I could have 1 and 2 in flask A and 3 and 4 in flask B. So that's 2 separate, energetically equivalent ways for those gases to disperse. And so if we look at all the unique ways for these gases to disperse, that would be, I would have six different ways. And so that means that state C, where I have 2 in each of the flasks, is 6 times greater the probability of finding gases in those systems. And so they have 6, so my W there would be 6. I have 6 energetically equivalent ways for those gases to distribute. And so from an entropy standpoint, that's going to be much favored over state A or B, where I only have one. So this is a really long-winded way of trying to explain entropy and how gases behave. Let's say I only have one energetically equivalent state. So let's say my W equals 1 as opposed to 6, and I only have one energy. That means that my S would be Boltzmann constant times ln W, and if W was 1, then this whole thing becomes 0. And so this is our third law of thermodynamics. This could only happen in a perfect crystal. Is the only time you could have an entropy value of 0. So basically you have 0 movement of those molecules. This is the third law of thermodynamics. So our first one was dealing with the total energy of the universe. Our second one was that if I have a spontaneous reaction, the entropy of the universe is always going to be increasing. And then my third law is if I have a perfect crystal at 0 degree Kelvin, W is going to be equal 1 and S will be 0. And this can never happen. I can't have a perfect crystal. So there's no such thing as a perfect crystal. So that means that my absolute entropy for any substance is going to be positive, right? We don't have that with enthalpy. Remember, we could look up values in the table for enthalpy, and some of them would be positive and some of them would be negative. If I look up values for entropy, they're always going to be positive. So entropy is always going to be positive because you can never have a perfect crystal, so I can never get to 0, and I'm certainly not going to get to negative. So entropy is always increasing. It's always going to be positive. But if I'm looking at the change in entropy, remember this is entropy final minus entropy initial, this can have a negative sign because this is a change. So my sign can be negative if my initial entropy state is greater than my final entropy state, or it can be positive if my final entropy state is bigger than my initial entropy state. So something where I've favored it from an entropy standpoint, it's going to be positive. So signs are going to be important. Enthalpy and entropy, my signs are going to be different in terms of when they're favoring and when they're unfavoring. So if I think about entropy, let's look at state changes as a function of entropy. So if I go from a solid to a liquid and a liquid to a gas, or solid all the way to the gas, I'm increasing my entropy, right? because I'm giving them more degrees of movement when delta S is positive. So as I move from a solid to a liquid to a gas, I'm unfavored from an enthalpy standpoint, but I'm favored from an entropy standpoint. And so my entropy is favoring that. The opposite happens here. So if I go this direction, now I'm decreasing the entropy. So my delta S here is going to be negative because I'm taking something that had a lot of movement, a lot of degrees and freedom of movement, and I'm constraining it into a solid phase. So delta S is negative here. And so just because something is favored from an enthalpy standpoint doesn't necessarily mean it's going to be favored from an entropy standpoint. So these would all be unfavored when delta S is negative. And these aren't always, so I can have some processes where I favor enthalpy and I favor entropy, and those are very spontaneous processes. I can have processes where I'm unfavored from an enthalpy standpoint, but I'm favored from an entropy standpoint, and I could have any of those combinations. And so we're going to pick up with that in part 2 and talk more about this concept. So I will see you then.